Chapter 10. Cardiovascular Function Reframed. Cardiovascular function is defined by the ability of blood vessels to maintain controlled flow, pressure distribution, and exchange across a continuously adapting network of boundaries. This system is often reduced to flow rates, pressure measurements, and circulating markers, but these outputs are downstream of structural conditions within the vessel wall. The endothelium and surrounding lipid membranes determine how signals are received, how the vessel responds to mechanical force, and how exchange with the bloodstream is regulated. When structure is stable, flow remains controlled and responsive. When it is not, the system shifts toward instability, where pressure, resistance, and signaling become inconsistent. The vascular endothelium forms the primary interface between blood and tissue. This layer is not passive. It acts as a dynamic membrane system that senses shear stress, chemical signals, and changes in circulating substrates. Lipid composition within endothelial membranes determines how these signals are translated into functional responses such as dilation or constriction. Stable membrane domains support consistent receptor activity and coordinated signaling pathways. Disruption alters how these inputs are processed, leading to responses that are either exaggerated or insufficient relative to the demand. Flow regulation depends on the ability of vessels to adjust diameter in response to local conditions. This adjustment requires rapid communication within the endothelial layer and between the endothelium and smooth muscle cells. Membrane integrity supports the propagation of these signals by maintaining receptor alignment and ion channel function. When structural consistency is lost, signal transmission becomes uneven and changes in vessel diameter occur with less precision. This introduces variability into blood flow, even if overall pressure remains within a measurable range. Exchange across the vascular boundary is also structurally controlled. Nutrients, gases, and signaling molecules must move between blood and tissue through regulated pathways. The permeability of this boundary depends on tight junctions and membrane organization. When lipid structure is maintained, exchange occurs selectively, allowing necessary substrates to pass while retaining structural integrity. Increased permeability due to membrane disruption allows uncontrolled movement of substances, altering the composition of both blood and surrounding tissue. Mechanical forces act continuously on the vascular system. Shear stress from blood flow and pressure from circulation require vessels to maintain structural resilience. Lipid composition influences how membranes respond to these forces, affecting their ability to deform and recover without damage. Stable membranes distribute mechanical stress evenly, preserving function. Structural drift creates regions of weakness where stress is not managed effectively, leading to localized dysfunction. Signal integration within the cardiovascular system depends on membrane-mediated processes. Hormonal signals, neural input, and local chemical cues all converge on the vessel wall. The endothelium processes these inputs and determines the appropriate response. When membrane structure supports organized signaling, these inputs are integrated into a coherent output. When it does not, signals compete or interfere with one another, leading to inconsistent regulation of vascular tone and flow. Energy demand within vascular cells is tied to their ability to maintain gradients and respond to continuous stimuli. Mitochondrial efficiency supports these functions, and this efficiency depends on membrane integrity within the organelle. Reduced efficiency limits the capacity of vascular cells to sustain their regulatory roles, contributing to functional instability under stress. Cardiovascular function therefore reflects the structural condition of the membranes that define the vessel wall. Flow, pressure, and exchange are emergent properties of this structure. When lipid organization is maintained, the system operates with controlled adaptability. When it is compromised, variability increases across multiple parameters because the boundaries that enforce coordinated behavior no longer maintain the conditions required for stable function. Blood vessels as lipid-regulated systems. Blood vessels operate as boundary systems whose behavior is determined by the structure of the endothelial membrane and the lipid environment that supports it. Flow, pressure, and exchange are outputs that emerge from how this boundary senses mechanical force, organizes signaling inputs, and controls permeability. The vessel wall is not a rigid pipe. It is a responsive surface that adjusts continuously based on conditions within the blood and the surrounding tissue. Lipid composition within this surface determines whether these adjustments occur in a controlled and coordinated manner or drift into inconsistency. The endothelium detects shear stress from flowing blood and converts it into biochemical signals that regulate vessel tone. This conversion depends on receptors and ion channels embedded within the membrane, positioned within lipid domains that support their function. When these domains are stable, shear stress produces predictable activation of pathways that lead to dilation or constriction. Changes in membrane composition alter how these forces are detected and processed. The same mechanical input can produce different outputs if receptor behavior shifts due to changes in the surrounding lipid environment. Nitric oxide production is one of the primary outputs of endothelial signaling and depends on membrane conditions that support enzyme activation and substrate availability. The enzyme responsible for its production operates within a lipid context that determines its efficiency and responsiveness. Stable membranes allow consistent production in response to flow, promoting smooth adjustments in vessel diameter. Structural disruption alters this process, leading to reduced or irregular production and affecting the ability of vessels to regulate resistance. Permeability of the vessel wall is governed by tight junctions and membrane organization. Lipid composition influences how closely cells adhere and how selectively substances can pass between them. When membranes maintain integrity, permeability remains controlled, allowing nutrients and gases to move as needed while preserving separation between blood and tissue. Structural changes increase permeability, allowing components to move across the boundary in an uncontrolled manner. This alters local environments and affects signaling within both compartments. Communication between endothelial cells and smooth muscle cells depends on membrane-mediated signaling. Signals generated at the endothelial surface must be transmitted across the vessel wall to produce changes in contraction. This requires consistent receptor activity and ion movement, both of which depend on membrane structure. When lipid organization supports these processes, signals propagate effectively, and the vessel adjusts its diameter in alignment with demand. When it does not, communication becomes uneven and regulation of tone loses precision. Mechanical resilience of blood vessels is also tied to lipid structure. Membranes must withstand continuous deformation as pressure and flow fluctuate. Lipid composition determines how well membranes can absorb and distribute these forces without sustaining damage. Stable membranes maintain their properties under stress, preserving function. Structural drift creates variability in how different regions respond to the same force, leading to localized changes in behavior. Energy production within vascular cells supports their ability to maintain gradients and respond to signaling inputs. This depends on mitochondrial membranes that sustain efficient ADP generation. When mitochondrial structure is intact, energy supply meets demand, allowing continuous regulation of vessel function. Reduced efficiency limits this capacity, making the system more sensitive to fluctuations in input. Blood vessels therefore function as lipid-regulated systems where structure defines behavior. The endothelial membrane integrates mechanical, chemical, and electrical inputs and converts them into coordinated outputs that control flow and exchange. When lipid organization is maintained, this integration produces stable and adaptive function. When it is not, variability emerges across the system because the boundary that governs these processes no longer maintains consistent conditions. Endothelial membranes and flow dynamics. Flow dynamics emerge from how endothelial membranes sense shear, organize signaling, and control ion movement along the vessel wall. The surface facing the bloodstream is a continuous lipid boundary that converts mechanical force into coordinated biochemical output. Shear stress deforms a membrane and its attached structures, shifting the state of embedded receptors and channels. When lipid packing and domain organization are stable, this deformation produces a consistent signal that aligns enzyme activity, ion flux, and downstream responses. The vessel adjusts diameter in proportion to flow, maintaining distribution without oscillation. When membrane structure drifts, the same mechanical input produces variable signaling, and flow becomes uneven across segments that should behave as a single unit. Mechanotransduction depends on spatial organization within the membrane. Receptors, adhesion complexes, and ion channels must be positioned within domains that preserve their coupling to cytoskeletal elements and signaling enzymes. Lipid composition determines whether these domains remain intact under continuous shear. Stable membranes keep these components aligned so that force applied at the surface is transmitted into a defined intracellular response. Disordered membranes uncouple this chain. Force is still applied, but it does not propagate through the same pathways with the same intensity, leading to inconsistent activation of downstream processes. Ion movement at the endothelial surface shapes immediate responses to flow. Calcium entry follows mechanical stimulation and acts as a trigger for pathways that adjust vessel tone. The magnitude and localization of this calcium signal depend on membrane permeability and channel positioning. When structure supports tight control, calcium influx is rapid and localized, producing a precise response. Increased permeability or altered channel distribution spreads this signal or reduces its peak, weakening the coupling between shear detection and functional output. Production of vasoactive mediators is tied directly to these membrane events. Enzymes responsible for generating signals that relax or constrict the vessel operate within specific lipid environments that influence their activity. When membranes maintain proper composition, these enzymes respond proportionally to shear, producing a stable relationship between flow and vessel diameter. Structural disruption alters enzyme responsiveness, shifting this relationship and introducing variability in how vessels react to the same conditions. The continuity of the endothelial layer allows signals to propagate along the vessel. Cells communicate through junctions and membrane-associated pathways that transmit changes in state from one region to another. Lipid organization supports this propagation by maintaining consistent membrane properties across cells. When these properties vary, signal transmission becomes uneven and coordination along the vessel is lost. Local segments may respond differently to the same flow, creating irregular patterns of resistance. Mechanical stress interacts with membrane structure over time. Continuous exposure to shear requires the membrane to deform and recover without losing integrity. Lipid composition determines how well this cycle is sustained. Stable membranes maintain their properties under repeated stress, preserving consistent signaling. Structural drift leads to cumulative changes in how the membrane responds, altering sensitivity to shear and shifting flow dynamics even without changes in external conditions. Energy availability influences the ability of endothelial cells to sustain these processes. Maintaining ion gradients, producing signaling molecules, and preserving membrane organization require continuous ADP supply. This depends on mitochondrial membranes that support efficient energy production. When energy production becomes less efficient, the system prioritizes basic maintenance over precise regulation, reducing the fidelity of flow control. Flow dynamics therefore reflect the state of endothelial membranes as sensing and response surfaces. Mechanical input from blood movement is translated into biochemical and electrical outputs through lipid-dependent processes. When membrane structure is intact, this translation remains consistent and flow is regulated smoothly across the vascular network. When structure is compromised, the link between force and response weakens, and flow becomes irregular because the membrane no longer enforces a stable relationship between input and output. Cholesterol transport as repair logistics. Cholesterol transport operates as a continuous repair system that moves structural material to sites where membranes require reinforcement or reconstruction. Cells do not treat cholesterol as excess cargo to be removed. They treat it as a component that must be redistributed to maintain membrane stability under changing conditions. Circulating lipoproteins act as transport vehicles that carry cholesterol through the bloodstream, delivering it to tissues where structural demand exceeds local supply. This movement is guided by signals that originate from membrane stress, damage, or increased mechanical load. The process begins when cells alter their surface properties in response to structural need. Receptors at the membrane recognize circulating lipoproteins and initiate uptake based on these signals. This is not a passive accumulation. It is a targeted response that depends on membrane condition. When structural integrity is intact, uptake remains controlled. When membranes experience stress or disruption, receptor activity increases, directing more cholesterol into the cell. The system responds to structural demand rather than arbitrary concentration gradients. Once internalized, cholesterol is routed toward membranes that require reinforcement. It integrates into the lipid bilayer, affecting packing density, permeability, and mechanical strength. Increased cholesterol content reduces free movement within the membrane, tightening structure and limiting ion leakage. This improves the ability of the membrane to maintain gradients and support embedded proteins. Redistribution within the cell ensures that areas under the greatest stress receive the highest concentration of structural material. Transport in the opposite direction also reflects structural conditions. Cells release cholesterol when membrane composition shifts toward excess rigidity or when structural balance is restored. Lipoproteins that collect cholesterol from tissues carry it back through the circulation for reuse or processing. This bidirectional movement maintains equilibrium across the system, preventing localized accumulation while ensuring availability where needed. The vascular system serves as the pathway for this logistics network, and endothelial membranes influence how lipoproteins interact with vessel walls. When endothelial structure is stable, transport occurs without significant retention. Lipoproteins pass through or interact transiently as part of normal exchange. Structural disruption alters this interaction. Changes in membrane permeability and receptor behavior can increase retention within the vessel wall, reflecting a local demand for repair material rather than a failure of transport. Inflammatory signaling modifies this system by increasing the demand for cholesterol at sites of membrane damage. As lipid breakdown generates signals that recruit repair processes, lipoprotein uptake rises in affected regions. This links cholesterol transport directly to the state of membrane integrity. Persistent signaling maintains elevated transport, sustaining delivery as long as structural disruption continues. Energy availability supports these logistics by enabling receptor function, vesicle trafficking, and intracellular redistribution. Efficient mitochondrial membranes provide the ADP required to maintain these processes. Reduced energy supply limits the ability of cells to manage cholesterol movement effectively, slowing repair and altering distribution patterns. Cholesterol transport therefore functions as a repair network that responds to structural conditions across tissues. Lipoproteins deliver and retrieve material based on membrane demand, maintaining balance through continuous redistribution. When membrane integrity is stable, this system operates quietly in the background. When structure is compromised, transport intensifies in affected areas because the system is responding to the need to restore the physical properties required for controlled cellular function. Plaque as a response, not a cause. Plaque formation begins as a localized response to disruption within the vascular boundary, not as an initiating event that drives dysfunction. The endothelium maintains separation between blood and tissue through a structured membrane that regulates permeability, signaling, and interaction with circulating particles. When this structure is compromised, the vessel wall shifts from a controlled interface to a reactive environment. Lipoproteins that normally transit through circulation begin to interact more directly with the vessel wall, not because they are inherently problematic, but because the boundary conditions that govern their movement have changed. Disruption of endothelial membranes alters permeability and receptor behavior. This allows lipoproteins carrying cholesterol to enter or remain within the vessel wall in areas where structural integrity has weakened. Once present, these particles provide material that can be used for repair. Cholesterol integrates into local membranes, increasing packing density and reducing permeability in an attempt to stabilize the disrupted region. This accumulation reflects a functional response to structural need. The system directs available resources to reinforce areas where the boundary has failed to maintain its normal properties. Inflammatory signaling accompanies this process because membrane disruption generates lipid-derived signals that recruit cellular activity. Immune cells enter the region and begin processing the accumulated material, interacting with both damaged membranes and retained lipoproteins. This activity is driven by the same signals that indicate structural damage. As long as these signals persist, the response continues and the accumulation of material within the vessel wall increases. Mechanical forces shape how this response develops. Regions of the vascular system that experience irregular flow or higher mechanical stress are more likely to exhibit structural disruption. These areas show increased interaction between lipoproteins and the vessel wall because the membrane must handle greater deformation and stress. The response in these regions reflects the need to stabilize a boundary that is under continuous strain. Over time, repeated cycles of disruption and repair lead to the formation of a more permanent structure within the vessel wall. This structure contains lipids, cellular material, and extracellular components that together act as a reinforcement of the affected area. The persistence of this structure indicates that the underlying conditions driving the response have not been resolved. The system maintains a repair state because the boundary continues to experience stress or instability. Energy availability influences the progression of this process. Cells involved in repair require ADP to maintain membrane integrity, process lipids, and manage signaling. Reduced mitochondrial efficiency limits the ability to complete repair cycles, prolonging the presence of intermediate states where accumulation continues without full resolution. This sustains the environment that supports plaque formation. Plaque, therefore, represents a structural adaptation to ongoing disruption within the vessel wall. It forms as part of an attempt to restore stability in areas where the endothelial membrane has lost its ability to maintain controlled separation and signaling. The presence of plaque reflects the history of repeated repair responses rather than serving as the initial driver of dysfunction, because the system is responding directly to the loss of structural integrity at the vascular boundary.